All right, welcome everyone. Today we're going to be looking at the idea of absolute convergence. So there's actually one more series test hidden in here. So that's what we're going to be looking at first. We're going to see how to use this idea of absolute convergence to show that a series is convergent. And then we'll be kind of introducing some terminology. So we'll see how to determine if a series is absolutely convergent, conditionally convergent, or divergent. So a little bit of new terminology here. So let's get into it. Let's look at our test. We call this the absolute convergence test. And the way it starts is we're given a series, sigma an. This is the series that we're trying to determine what happens. Does it converge or does it diverge? Can we add the terms together, essentially? That's what we're interested in. Does it make sense to add all these terms together? Do we get a finite sum? So we're interested in this series. Is this series convergent or divergent? And what we're going to do is we're going to look at this related series, this series with the absolute value terms. So sigma absolute value an. So first, let's just look at what these kind of two series look like. So we have our original series, and this is what we're interested in. So this is sigma an. And let's say we start with n equals 1, but this idea would work if we had a other starting index. But let's just say this starts at index 1. And just to get an idea of what this new related series looks like, let's write out the first few terms. So what would this series look like? It would be a1 plus a2 plus a3 and so on. So we're just adding up some terms here. Now this series of absolute values, what does that look like? Let's write it out. So this is going to be the sum from n equals 1 to infinity. Again, this test works if we have other starting index values, but let's start this one at n equals 1 just to get a little example here. And we're going to have the absolute value of an. So we're doing the series of the absolute value terms here. What is this series? What does this look like if we write out the first few terms? So the first one, instead of a1, would be absolute value a1. The second piece would be a2, but it's not just a2, it's the absolute value of a2, and so on. Then we have absolute value of a3, and then this keeps going. So, the idea here is potentially in our original series, some of these a values might be negative. So these terms here might be, some of them might be positive, some of them might be negative. So, some of these a values are positive, some of them are negative. Potentially. Depends on the series. But there could some of them could be negative. Now, when we go to our series of absolute values here, because we're doing the absolute value of all of these terms individually, every single term here is going to be positive. So all of these are positive here. All right, so what this test does is it gives us another way to deal with series that might have some negative terms. So we've already seen one of these. So most of the tests that we've used, let's go through them. Integral test. The integral test, we needed our terms to be positive. the comparison test, we needed our terms to be positive. The alternating series test, that was one that we could have negative terms, but it had to have a very specific alternating pattern. Positive, negative, or negative, positive, negative, positive. So it had to have that alternating pattern. Here, this is a little bit kind of more relaxed. So it doesn't necessarily have to have that exact alternating negative, positive pattern. Just some of them might be negative, some of them might be positive. So it's a little bit more relaxed. And then we had the ratio test and the root test. And those also could allow negative terms because we were doing the absolute value there as well. So this is just another test. If we have negative terms, this is another test that might help us deal with those. So what does the test actually say? So we have our original series sigma an. This is just the original series we're testing. We're looking at this new series, the series of absolute value terms, sigma absolute value an. Everything is positive here. And so if sigma absolute value an, if this new series converges, then our original series, sigma an, must converge as well. If sigma absolute value an diverges, then the test is inconclusive. It doesn't really tell us what's happening with sigma an. That might converge, it might diverge. So the way we use this generally is this first statement here, where if we find out that this series of absolute values, if that converges, well, then we can automatically conclude that our original series converges as well. All right, so let's try out an example. Let's look at example 1. We're going to determine if this series is convergent or divergent. So this is the series sigma n equals 1 to infinity of negative 1 raised to the power n over n squared. And we see this negative 1 raised to the power n. So we could, and we probably did, use the alternating series test to show that this is convergent. So that is one perfectly acceptable way to do this. So just make a note of this. We could use the alternating series test here because we see that alternating piece. So what would we need to show for the alternating series test? There are two things. The limit of Bn as n goes to infinity is equal to 0. And then you also need to show that the sequence Bn is decreasing. So Bn plus 1 is less than or equal to Bn. So you could go through that. That's a perfectly reasonable test to use here because we see that alternating piece. So this is an alternating series. You would just have to identify Bn, show that the limit of Bn is equal to 0, and then show that Bn plus 1 is less than or equal to Bn. Perfectly fine to do that. We're just going to use this absolute convergence test, just as another way to think about these. So let's try it out. So and maybe it helps to write out the first few terms here, just to see what this looks like. So what's the first term when n is 1? Well, we get negative 1 over 1 squared. Then when n is 2, we get positive 1 over 2 squared. And then we get negative 1 over 3 squared and positive 1 over 4 squared and so on. So we have this, it's an alternating series, negative, positive, and then we've just written out the first few terms. What we're going to do, and this is sigma an. This is our original series that we're interested in. For the absolute convergence test, we're going to look at kind of the related series the series with the absolute values. So we're going to apply the absolute value there. So what would this look like? Well, it would be the absolute value of negative 1 raised to the power n over n squared. And this alternating piece goes positive, negative, positive, negative. So sometimes it's positive, sometimes it's negative. The absolute value doesn't care. It's going to always make that thing positive. And then n squared is always positive. So we could really rewrite this as 1 over n squared. It's equivalent. The absolute value essentially cancels off that alternating piece. And then n squared is always positive. And we know what this series is. So this is a convergent p-series with p equal to 2, which is greater than 1. So we know this is one of our our basic form series. This is a p-series, and we know it's convergent because the p-value, which is 2, is greater than 1. Just as a little practice here, let's write out the first few terms. So what do the first few terms look like here? Well, it's basically everything that was here, just everything's positive. So the first term would be 1 over 1 squared, then plus 1 over 2 squared, plus 1 over 3 squared, plus 1 over 4 squared, and so on. So it's the same kind of terms here. It's just we've done the absolute value of everything, so all those negatives just became positive. All right, so we know that sigma absolute value an is a convergent p-series. So that means our original series also converges. So since sigma absolute value an, the series of absolute value terms, converges, the original series, sigma an, must also converge. By the absolute convergence test. So what we did is we were given this original series that had some alternating pieces here. Instead, we looked at a related series, not the exact same series, but a related one, this sigma absolute value an, and saw that it was a convergent p-series. And because this series converged, we were able to conclude that our original series also converged by the absolute convergence test. So, sometimes this can be a little bit quicker than doing the alternating series test. But again, that would be just another way to do this one. We could have just shown it directly by the alternating series test. That would have also been perfectly fine. All right, so there's something special here about when this new series, sigma absolute value an, converges. So we want to develop some terminology for when this happens. So it doesn't always happen, and we'll see some examples where this does not happen. This absolute value series does not converge. So we want to develop some special terminology, and we're going to introduce two definitions. So we say a series sigma an is absolutely convergent if both sigma an and sigma absolute value an are both convergent. Now, what happens if this absolute value series, what happens if this diverges? Well, then we say our series is conditionally convergent. So we say a series sigma an is conditionally convergent if it converges, but that absolute value series diverges. So we have these two definitions, absolutely convergent and conditionally convergent. So it kind of helps to think, what are all the possible options here? So we're kind of working with two distinct series, potentially distinct. I guess we should go back and add here to the beginning that, if everything is positive in our original series, then this really isn't interesting, because if everything's positive, when we do the absolute value, it's all still going to be positive. So another note here. Let's add this in. If AN are all positive, then sigma AN is equal to sigma absolute value AN. The absolute value doesn't really do anything then. So we're really talking about the same series here. So really this idea of absolute convergence is most interesting when there's some kind of negative component to it, to our series. Some of the terms are negative. All right, so we have our first definition here. And let's go through and think about what are all the potential options. We have two different series here. So we could have sigma AN be convergent. We could have sigma AN be divergent. Those are the only two options for sigma AN. It's either convergent or it's not. It's divergent. Same thing with the other series. The series of absolute value terms. This could either be convergent or it could be divergent. And let's just think about, related to these definitions of absolute convergence, conditional convergence, what's going on. So let's do this little chart here. So what happens if both sigma AN and sigma absolute value AN are convergent? So what happens if both of them are convergent? Well, that's what we call absolutely convergent here. And this is really what our absolute convergence test says. So if the absolute value, if this series of absolute value terms converges, well then this one has to automatically converge. And in which case, if both of them are converging, we say it's absolutely convergent. Sigma AN is absolutely convergent. All right, so what happens if the absolute value terms are convergent? That series is convergent, but our original series is divergent. Well, this can't happen. So this cannot happen by our test, our absolute convergence test. So if this series of absolute value terms is convergent, then automatically sigma AN has to be convergent as well. So this cannot happen. We can't have this series be convergent and this series be divergent. Just can't happen because of that absolute convergence test. Now what we can have is, in the case where this absolute value series diverges, well, we said the test was inconclusive. And the reason is it's inconclusive is because sigma AN might converge, it might still diverge. So in the case where this absolute value series diverges, if sigma AN converges, then we call that conditionally convergent. And if both series diverge, well then we just say it's divergent. So those are really the three kind of potential cases here for what's happening with this idea of absolute convergence. So if both of these related series converge, then it's absolutely convergent. If this absolute value series diverges, but our original one still converges, which can happen, we say it's conditionally convergent. And then if both diverge, then we just say it's divergent. All right, so that's hopefully gives you an idea of what these different terminology mean here and in what cases they become applicable. Let's try an example. we're going to look at example 2. And we're going to determine if this series is absolutely convergent, conditionally convergent, or just divergent. So this is the series sigma n equals 1 to infinity of -1 raised to the power n over n. So this is an alternating series. And we want to know, is it absolutely convergent, conditionally convergent, or divergent? So to start, and again, it helps to remember, this is just our original series. So this is sigma an. We're going to start by looking at the series of absolute value terms. So let's write out what that looks like. So we're doing the absolute value of an here. That's just the series of absolute value terms. Let's write it out specifically for our series. So from n equals 1 to infinity, now we're applying the absolute value to everything, to each individual term. And again, we have this alternating piece, -1 raised to the power n. Just bounces back, negative, positive, negative, positive. But the absolute value doesn't care. So it's always going to make this positive. And n is always positive because it's greater than or equal to 1. So what happens is essentially the absolute value here really just cancels off that kind of alternating piece. And we're left with just the sum from n equals 1 to infinity of 1 over n. And this is just our harmonic series, or p series with p equal to 1. So we know what this series does. This is a divergent p series with p equal to 1. And we know that when the p values are less than or equal to 1, it's a divergent p series. So we're just providing some explanation about why this series diverges here. All right, so what we see here is we have our original series. We still don't know if this thing converges or diverges, but we know that the series of absolute value terms diverges. So the absolute convergence test is inconclusive. So when we get that this series of absolute value terms diverges, it doesn't tell us anything about what's happening to our original series, unfortunately. So we have to go on. And this is an alternating series test. So we're going to look at the convergence then of our original series. And we've done this one before, actually. This is an alternating series. So we've actually shown, using the alternating series test, that this thing converges. So we've actually shown this. So normally you would have to go through and show those steps, show those conditions for the alternating series test. We've done this one in a previous example. So, you can either go back and try this for yourself, or just go back and look at what we did when we talked about alternating series. So we've done this one before. All right, so what do we have here? We showed that the series of absolute value terms was a divergent p series, but we've shown that our original series is a convergent alternating series, and we use the alternating series test for that. So what do we have? We have this sigma absolute value an divergent, sigma an convergent. So what this means is our original series, we know it's convergent, but we also say it's conditionally convergent. So if we go back to our definition, what was our definition for conditionally convergent? It's where our original series converges, but the absolute value series diverges here. And that's what we're said. So our original series converges, but our absolute value series diverges, so it makes this thing conditionally convergent. All right, let's try one more example. Example 3. We're going to determine if this series is absolutely convergent, conditionally convergent, or divergent. So it's the sum from n equals 1 to infinity of -1 raised to the n minus 1 power over 3 to the n plus 1. So we start just like we did in example 2. We start with our series of absolute value terms. All right, so here is our original series, sigma an. We're going to look at sigma absolute value an. So let's write it out. Let's apply the absolute value sign. So we're going from n equals 1 to infinity. Apply the absolute value sign. And 3 to the n is positive because n is, well, it's an exponential function. Exponential functions are always positive. But also n is greater than or equal to 1. We're adding 1, so everything is positive in the denominator. We have this alternating piece in the numerator, so, it goes plus minus, plus minus. But the absolute value cancels that off. And so we're left with then, what are we left with? The sum from n equals 1 to infinity of 1 over 3 to the n plus 1. And kind of cheating here, we've looked at this one in a previous example. So we know this is convergent. By the comparison test. So again, we've looked at this series before. So normally if you were doing this one and this was just a brand new series that you were doing, you would have to go through then and show, use the comparison test and show that this is convergent. We did this exact one back when we talked about the comparison test. So go back, try it again or go back through that example to see how we showed it. So just a little disclaimer here. Normally you would need to show all your work. But we've done this one before. But normally there's going to be some more work here. You'd go through all the steps of the comparison test. What did we compare this to? Well, we compared it to the geometric series 1 over 3 to the n. So it wouldn't be a math class if, I said do this for homework or something like that, left as an exercise. Get away with it. All right, so we've done this one before. We know this is a convergent convergent series by the comparison test. Or you could use the limit comparison test. That would also work. All right, so what that means is we're done. We know this thing is convergent. We know the series of absolute value terms is convergent. So then automatically, we don't even have to do anything here. Automatically, by the absolute convergence test, we know sigma an converges as well. We know our original series converges. So because we were able to show that the series of absolute values term converges, we're able to do that with the comparison test. We showed that this thing is convergent. automatically by the absolute convergence test, we know sigma AN converges as well. So this is all we need to do for our original series sigma AN. So we know this original alternating series, we know this converges, and then we also know that our series of absolute value terms, that converges as well. So we can say then sigma AN here is, not only is it convergent, but it's absolutely convergent. So when both of these series converge, our original series and then the series formed from the absolute value terms, sigma absolute value AN, when both of those converge, we say our original series is absolutely convergent. So this is it's a stronger condition that we know that in either case here, this series converges. All right, so that's really going to do it for our last kind of test for testing a series for convergence. So next time, what we're going to be looking at is we're going to be getting into the idea of power series. So we're still going to be talking about series. We're still going to be using a whole bunch of series tests, but now we're going to see where we actually apply these tests. So that's going to be coming up in the next lesson. So we'll see you then. Bye-bye.